Welcome back to the Deep Dive. Great to have you with us again as we, really get into the weeds of complex tech topics.
Glad to be here.
I'm your host. In our last deep dive, we looked at intelligent agent architectures, sort of the blueprints for AI agents.
That's right.
Today, we're building right on top of that. We're exploring something absolutely fundamental to how AI actually does things in the world. We're diving into planning and goal-oriented behavior of AgenticAI.
Absolutely. And it's such a key topic because, well, think about it. An agent that can't plan, it's just reacting, isn't it? Moment to moment.
To bouncing off things.
Exactly. But planning is what elevates it. It turns a simple reactive program into something proactive, something goal-directed.
Okay.
It's really the art of foresight. It's that deliberate process of figuring out, okay, here's where I am, here's where I want to be. How do I string actions together to get there?
It's like the cognitive bridge, connecting the what I want with the how I get it.
That's a great way to put it. A cognitive bridge. Perfect. It really marks that shift towards, well, something more like intelligence.
Right. And to help us cross that bridge today, we've got a clear roadmap laid out. We're going to tackle a series of specific questions, taking us from the basics all the way through to, more advanced ideas and real-world stuff.
Exactly. We want to be thorough. Planning is a big area, so we've broken it down. Here's a quick rundown of the questions we'll be digging into.
So let's hear it.
First, what does an agent even need to know before it can start planning?
Right. The prerequisites.
Second, we hear about utility. How does that make agent behavior more, let's say, sophisticated?
Beyond just achieving the goal.
Precisely. Third, what is this foundational classical planning model called STRIPS?
Heard of it? Yeah. The classic.
Fourth, how does STRIPS actually represent the world state, the available actions, and the goal itself?
The nitty-gritty of the representation.
Fifth, okay, given that STRIPS model, how does a planner actually find the sequence of actions? What's the process?
The search part.
Sixth, classical planning isn't always efficient. So what's Hierarchical Task Network, or HTN planning, and how does it sort of mimic how humans think?
The human-like approach. Interesting.
Seventh, and how does HTN use these high-level tasks and methods to break problems down?
The mechanics of HTN.
Eighth, what are the big advantages of using this hierarchical way of thinking?
Why bother with HTN?
Ninth, we need a common language, right? So what is PDDL and why is it so important for planners?
PDDL, the standard.
10th, how does PDDL cleverly separate the physics of a world from a specific problem?
Domain versus problem. Got it.
11th, what about other approaches like logic-based tools, maybe PyDatalog? What are those?
Logic programming for planning.
12th, okay, real world now. How does a robust agent juggle multiple goals, especially when they conflict?
Priorities. Yeah.
13th, and what happens when things go wrong? You have a plan, it fails. What's replanning?
Handling failure. Crucial.
And finally, 14th. Let's wrap it up. What are the key takeaways about foresight and goal-directed behavior in these agents?
Okay, fantastic. That's a comprehensive roadmap.
It covers a lot of ground.
It does indeed. So let's dive straight into question 1. You mentioned planning elevates an agent. What's that absolute first thing, that foundational piece of knowledge an agent needs before it can even start planning?
Yeah, excellent place to start, because without this, the whole exercise is pointless, really. Before an agent can figure out how to do something, it absolutely must know what it's trying to achieve. What's the point?
Makes sense.
And this initial step, this defining of the objective, is called goal formulation.
Goal formulation. Okay.
It's basically the process of defining what counts as a good outcome for the agent in its world.
Defining success.
Exactly, defining success. And in its simplest form, a goal is just a description of the state or set of states of the world that the agent finds desirable. So take our package delivery drone example. A very clear goal might be expressed as a condition at drone location B, A and D. At package location B.
Super specific. Drone at B, package at B.
Precisely. It's binary. Either you're in that state or you're not. This kind of clear-cut yes or no goal is very common in what we call classical planning. The objective is unambiguous.
It answers the where are we going question first.
Absolutely, before you can even think about the route.
I see. So goal formulation sets the destination. But you hinted earlier, and the source material mentions, that just reaching the goal isn't always the whole story. This brings us to question 2. How does this idea of utility lead to more, let's say, sophisticated or nuanced behavior?
You've hit on a really critical point there because, yeah, just getting to location B might be the goal, but in the real world, well, some ways of getting there are definitely better than others, aren't they?
Faster, maybe. Cheaper, safer.
Exactly. All of those. Faster, safer, more energy efficient, you name it. This is where utility comes into play. A utility function basically assigns a number, a score, to a state, or maybe even a whole sequence of states that quantifies how desirable it is.
So it's not just goal achieved.
Yeah.
Yes, no. It's how well did we achieve it, maybe.
Precisely. It moves way beyond that simple binary. It allows for much finer-grained decision-making.
How would that work for the drone, then? Can you give an example?
Sure. Let's stick with the delivery drone.
Ah.
Its utility function wouldn't just look at arrival. It might be set up like this. You get, say, plus 1,000 points for a successful delivery. Big reward.
Okay, makes sense.
But then you start subtracting points. Maybe manic 1 point for every minute of flight time that encourages speed.
Right.
Maybe manic or 10 points for every unit of battery consumed. That pushes for efficiency.
Ah, the trade-off.
Exactly. And maybe a big penalty, like manic at 500 points for flying through a known high-risk weather zone. That's for safety.
Got it. So you're adding up the good stuff and subtracting the costs or risks.
That's the idea. And the agent's planner is then instructed not just to reach the goal, but to maximize this total utility score. So it won't just find any path. It'll actively search for the best path, the one that gives the highest score, by balancing speed, efficiency, safety, whatever factors you build in.
So goal formulation defines the destination.
Yep.
And the utility function defines the quality of the journey to that destination.
Beautifully put. Exactly. Yeah. It's the difference between just getting there and getting there optimally.
That makes a lot of sense. It adds that layer of real-world practicality. Okay, so with goals and utility in mind, let's shift to the mechanics. Question 3. What is this classical planning model known as STRIPS? Why is it considered so foundational?
Right, STRIPS. You can't really talk about automated planning history without talking about STRIPS. It stands for Stanford Research Institute Problem Solver, developed back in the 1970s. And it was really pivotal. It introduced a way of representing planning problems that was so clear and effective that it basically became the standard. Its way of describing things heavily influenced almost all the classical planning work that followed.
So its main contribution was the representation?
Largely, yes. It provided a formal language, a structure for thinking about these problems that was simple enough for computers at the time to actually work with, but expressive enough to capture meaningful tasks. It kind of cracked open the door for automated planning.
Okay, foundational indeed. So, question 4 then. How does STRIPS represent those 3 key bits? The state, the actions, and the goal. What does that look like?
Okay, so STRIPS breaks it down very neatly. First, you have the state.
Right, the current situation.
Exactly. It's represented as a conjunction, basically an and-D list of positive literals. Think of them as facts that are currently true about the world.
Like what?
For example, at Robot Rooma and Holding Ball and Litus and Lavison. Just a list of true things.
Okay.
And crucially, STRIPS usually works under the closed world assumption.
Which means?
It means anything not explicitly listed as true in the state is assumed to be false. Keeps things manageable.
Got it. So that's the state. What about actions?
Okay. Actions sometimes called operators. Each action in STRIPS has 3 parts. First, the action signature, just its name and any parameters, like move from to Groomy. Simple.
Like move room a room.
Exactly. Second, the preconditions. This is a set of facts that must be true in the current state for you to even be allowed to perform the action.
You have to be able to do it.
Right. So for move room a room, a precondition might be at Robot Rooma, you have to be in room A, and maybe door open room, the door needs to be open.
Makes sense. And the third part?
The effects. This describes how the action changes the world state. And it has 2 lists. An add list and a delete list.
Okay, what becomes true and what becomes false?
Precisely. So for move room a room, the effect would probably be add at robot room, that becomes true, and delete at robot rooma, that's no longer true.
Okay, state. Actions with preconditions and effects. What about the goal?
The goal in STRIPS is pretty straightforward, too. It's just a set of facts, like the state representation that the planner wants to make true.
The desired end state.
Exactly. The planner's whole job is to find a sequence of these defined actions that transforms the initial state into any state where all the goal facts hold true.
Right. So you've got this neat STRIPS representation, initial state, actions, goal. Question 5. How does a planner actually find that sequence of actions? You mentioned it's not just trial and error. What's the method?
It's a search process. Essentially, it's search through the space of possible world states.
Okay, searching the state space.
Right. And one of the most fundamental ways to do this is called forward state space search.
Forward search. How does that work?
Well, you start, logically enough, at the initial state, the state you're currently in.
Makes sense.
Then the planner looks at all the actions whose preconditions are met in that current state, all the things it could do right now.
The applicable actions.
Exactly. For each of those applicable actions, it simulates taking the action by applying its effects, the add list and delete list.
Okay, creating a hypothetical next state.
Precisely. It generates these new successor states. And it keeps doing this, branching out from the initial state, then from the states it just generated, and so on.
It's building a tree.
It's building a search tree, yeah. Each node is a state, and each edge is an action. And it explores this tree level by level, or using some strategy, until it finds a node, a state, where all the goal conditions are true.
Oh, okay.
And the path from the root of the tree, the initial state, to that goal node is the sequence of actions that gets you there.
So it methodically explores possibilities until it finds a winning path.
That's a good way to think about it. It's systematic, even if it can be computationally intensive.
Right. I can see how that tree could get enormous for complex problems. Which leads perfectly into question 6. Classical planning can be inefficient. What is Hierarchical Task Network, or HTN planning, and how does it supposedly mimic human thinking to deal with that complexity?
Yeah, you're spot on. That exhaustive search in classical planning can really bog down. Imagine planning a trip from, say, Gatineau to Vancouver. You don't plan it by thinking, turn left, turn right, accelerate, brake for every single step, do you?
No way. I think, okay, get to the airport, then fly, then get to the hotel. Big chunks.
Exactly. Big chunks. You think hierarchically, first the high-level steps, then maybe you break those down. That's precisely what Hierarchical Task Network, or HTN, planning tries to capture.
Ah, okay. So it mirrors that top-down human approach.
It does. It aims to break down large, complex problems into smaller, more manageable sub-problems, just like we do naturally.
And that helps with the inefficiency.
Hugely. Instead of getting lost in tiny details from the start, it focuses the search using this hierarchical structure.
Yeah.
It's not just about speed, though. It often produces plans that feel more, well, logical or common sense from a human perspective.
Interesting. So question 7 then. How does it actually do that? How does an HTN planner use these high-level tasks and methods you mentioned to break down the problem?
Right. This is the core mechanism of HTN. Unlike classical planners that only deal with, let's call them primitive actions, the things the agent can directly execute.
Like move or pick up.
Exactly. HTN planners also work with high-level tasks, sometimes called compound tasks. These are more abstract goals, like your get to the airport example.
Okay, abstract goals. And the methods?
Methods are the key. A method is essentially a recipe or a procedure that describes one way a high-level task can be decomposed into a sequence of smaller subtasks.
Ah, like a subroutine or a plan template for that task.
Sort of, yeah. So for get at the airport, one method might be 1. Call a taxi. 2. Ride in the taxi to the airport. 3. Pay the driver.
Okay, a sequence of steps.
Right. Now, crucially, these subtasks like call taxi might themselves be high-level tasks that have their own methods for decomposition.
So it's recursive.
Exactly. It's recursive decomposition. Call a taxi might break down into find phone, open app, request ride, or a subtask could just be a primitive action like pay the driver.
I see.
So the HTN planner starts with the main high-level goal and keeps applying these methods, breaking tasks down into subtasks, until eventually everything is reduced to a sequence of only primitive executable actions.
It's building the detailed plan from the top down.
Precisely. Top-down refinement until you hit the ground level of executable steps.
That sounds much more structured.
Yeah.
So, question 8. What are the main advantages you get from taking this hierarchical approach compared to the classical flat search?
There are a couple of really significant advantages. The first, as we hinted, is efficiency, especially for complex problems.
Right. Avoids getting lost in the weeds.
Exactly. That hierarchical structure provides guidance. It drastically prunes the search space the planner needs to explore. Instead of considering every possible primitive action at every step, it focuses on relevant decompositions. It's like having, Major highways marked on your map instead of just a massive grid of tiny streets.
Good analogy.
Yeah.
What's the second advantage?
The second one is really powerful too. HTN allows domain experts, people who actually know how things are done in a particular field, to encode common sense procedures and strategies directly into the methods.
Ah, so you can bake in expertise.
Yes. You can tell the planner, look, when you need to achieve task X, this is usually a good way to break it down. This means the plans generated aren't just computationally found, they often reflect established best practices. They tend to be more logical, more intuitive, and frankly, more human understandable.
You're embedding human intelligence into the planning process itself.
That's a great way to put it. You're guiding the AI's search with human strategic knowledge.
Okay, very cool. So we have these powerful planning approaches, strips, and HTN. Now, for these planners to actually work together or for researchers to compare them, they need a common language, right? Question 9. What is PDDL and why is it important?
Exactly. You need a lingua franca. And in the world of automated planning, that's PDDL, the Planning Domain Definition Language.
PDDL, okay.
It has become the de facto standard. It's the language most researchers and developers use to describe planning problems so that various different planners can understand and attempt to solve them.
So it enables interoperability and comparison.
Precisely. It was actually developed initially to support the international planning competition, the IPC.
Ah, the competition needed a standard format.
Right. To benchmark different planning algorithms against each other, you need everyone working from the same problem descriptions. PDDL provided that standard. It's like the universal translator for AI planning tasks.
Makes sense. Universal translator. I like that.
Yeah.
Now, question 10 builds on this. The source material mentions PDDL cleverly separates the physics of a world from a specific problem instance. How does that work? What's the benefit?
Yeah, this separation is a really elegant and practical feature of PDDL. It splits the description of a planning task into two distinct files.
Two files, okay.
First, there's the domain file. Think of this as defining the laws of physics for a particular world or environment.
The general rules.
Exactly. It defines the types of objects that exist, like robots, rooms, keys, the predicates, like at holding door open facts that can be true or false, and crucially, it defines the actions.
Strips like actions.
Yep. Actions with their parameters, their preconditions, and their effects. This domain file describes the potential of the world, the rules of the game, you might say, and it's reusable for any problem set in that world.
Okay, so the domain file is the rulebook. What's the second file?
The second file is the problem file. This file describes a specific instance of a planning problem within that domain.
A particular scenario.
Right. It lists the actual objects that exist in this specific scenario, like Robot 1, Room A, Key 1. It specifies the initial state, exactly which facts are true at the very beginning. And it defines the goal state, the specific set of facts we want to achieve for this particular problem.
Ah, I see. So the domain is the general physics. The problem is the specific starting point and target.
Exactly. And the separation is brilliant because you can write one domain file for, say, logistics planning, and then test your planner on dozens of different problem files, different warehouse layouts, different delivery tasks without rewriting the fundamental rules every time.
Makes testing and development much easier.
Hugely. Very practical design.
Okay, so PDDL is the standard for strips and HTN-like planners. But question 11 asks about another approach mentioned, logic-based planning tools, like PyDatalog. What are these and how do they differ?
Right. So beyond the state-space search approaches we've mostly discussed, you can also tackle planning using logic programming.
Logic programming.
Like Prolog. Like Prolog, exactly. Or libraries like PyDatalog, which integrates logic programming concepts into Python.
Okay. How does that work for planning?
Well, in this approach, you represent the states and the effects of actions using logical facts and rules. An action might be a rule that says, if these facts are true, preconditions, then these other facts become true, and these ones cease to be true, effects.
So it's all expressed in logic.
Yes. And the planner itself then acts more like a deductive reasoning engine or a theorem prover.
Okay.
It tries to find a logical proof using the rules of the actions that demonstrates the goal state is reachable from the initial state. The sequence of rules used in that proof essentially is the plan.
Wow, so planning becomes proving a theorem.
In essence, yes, it's a different paradigm. It can be really powerful for problems with very complex logical constraints or relationships between objects, things that might be awkward to express purely in strips or PDDL.
Where might you see this used?
You might see it in areas like business process modeling or maybe complex multi-agent coordination tasks where the logical consistency of interactions is critical. It's maybe less common for, say, mainstream robotics navigation than PD deal-based systems, but it's a very valuable tool in the planner's toolbox for certain kinds of problems.
Interesting. A different way of thinking about finding a path. Okay, we've covered different ways to make plans. Let's move towards the messy reality. Question 12. The real world is unpredictable. Agents often have multiple goals. How does a robust agent handle having several goals, especially if they conflict?
Yes. The transition from the neat world of the planner to the chaos of reality. This is crucial. Real-world agents rarely have just one simple goal.
Right, like a robot needing to recharge, fetch something, explore.
Exactly. It needs to recharge its battery, fetch object A, maybe map a new area, just enter. It can't do all those things at the same time.
So what does it do?
It needs goal prioritization. There has to be a mechanism to decide which goal is most important right now.
How does it decide?
Often, this involves assigning some kind of utility value or an importance weight to each goal. But critically, and this is key for robustness, these priorities usually aren't static.
They can change.
They must be able to change dynamically based on the situation. Think about the recharge battery goal.
Yeah.
It might start as a low-priority background task when the battery is full, but as the battery level drops, its priority, its importance, needs to increase.
Until it becomes urgent.
Exactly. It might rise until it becomes the most important goal, overriding whatever else the robot was doing. Fetching object A can wait if the robot is about to die.
Right, survival first.
Pretty much. This dynamic goal prioritization, reacting to changing internal states and external circumstances, is absolutely fundamental for rational, adaptive behavior in the real world.
That makes perfect sense. Constant reevaluation of what matters most.
Okay, so even with prioritized goals, things can still go wrong during execution. Question 13. What happens when a well-laid plan hits a snag? What is this concept of replanning?
Yeah, this is where the robustness really gets tested because, like we said, a plan is just a hypothesis about the future.
A prediction.
A prediction. And predictions can be wrong. The real world doesn't always cooperate. So a truly intelligent agent needs to perform plan execution monitoring.
Watching itself execute the plan.
Basically, yes, it needs to check just before it takes the next step in its plan. Are the preconditions for this action actually met right now?
Verifying assumptions.
Exactly. And then, after it performs the action, it needs to check, did this action have the effects I expected it to have?
Did reality match the model?
Precisely. So what happens if the check fails? Let's say the plan involves going through a door, but the agent gets there and finds the door is unexpectedly locked. Precondition failure.
Okay, plan derailed. Now what? There are generally a couple of levels of response. The first is simple repair.
Patching the plan.
Kind of. The agent might try to find a quick local fix, like, okay, the door's locked. Is there an alternative action I can take right now to satisfy that door open condition? Maybe it has an action like find key or unlock door. If it can insert a small subplan to fix the immediate problem and then continue with the original plan, that's ideal.
A local patch. But what if it can't? Or if the world has changed too much?
Right. If the change is too drastic or a simple repair isn't feasible, the agent might have to resort to full replanning.
Starting over.
Essentially, yes. It basically throws away the rest of its current plan, takes stock of its new current state, including the locked door, and invokes the planner all over again to generate a completely new plan from this point forward to achieve its goals.
That sounds computationally expensive, but necessary sometimes.
It can be, but it's often the only way to recover from significant unexpected changes. This whole cycle dynamic, goal prioritization, execution monitoring, and the ability to repair or fully replan when things go wrong, that's what really separates a robust, real-world autonomous system from a brittle toy planner that only works in perfect simulations.
It's about resilience.
Resilience is the perfect word. Adaptability and resilience in the face of an imperfect world.
Fantastic. Okay, we've covered a huge amount of ground, from strips to HTN, PDDL, logic, goals, utility, and replanning. Let's try to synthesize this for question 14. What are the absolute key takeaways about foresight and goal-oriented behavior and intelligent agents that you want our listeners to really grasp from this deep dive?
Okay, the big picture. I think the absolute core takeaway is that planning is the cognitive engine that powers intelligent, goal-oriented behavior. It's not just about reacting, it's about looking ahead.
The foresight part.
Exactly. It's what allows an agent to reason about the future, to anticipate the consequences of its actions, and to actually formulate a strategy, a coherent sequence of steps to achieve what it wants.
Okay, planning is the strategic engine.
Right. And we saw how agents define what they want through goal formulation and how they can make more nuanced, sophisticated choices about how to get there, using utility functions to weigh different factors like cost, time, and risk.
Destination and journey quality.
Yep. We touched on the foundations with the classical STRIPS model, that essential language for describing states, actions, and goals.
The basic building blocks.
And then we saw how more advanced techniques like Hierarchical Task Networks, HTN, offer a more efficient and often more human-like way to tackle complex problems by breaking them down systematically, top-down.
Scaling up the planning.
And of course, the importance of standards like PDDL to make all this practical, allowing different planners to understand the same problems.
The common language.
But perhaps the most crucial takeaway, especially when we think about real-world AI, is this. A plan is only ever a hypothesis.
Right. Not gonable.
Not at all. It's a best guess about a future that is inherently uncertain. So the true measure of an agent's intelligence isn't just its ability to create a perfect plan and a perfectly predictable simulation.
It's how it handles reality.
It's how it handles reality's imperfections. It's that resilience we talked about, the capacity for dynamic goal prioritization, figuring out what matters most right now, and the ability for swift, intelligent replanning when the unexpected happens. That's what allows an agent to adapt, to persevere, and ultimately to succeed out there in the messy, unpredictable real world.
So foresight plus resilience.
Foresight combined with resilience, that's the essence, I think, of practical, goal-oriented intelligence. It's what makes AI truly useful beyond the lab.
That's a really powerful synthesis.
Yeah.
Planning provides the map, but intelligence includes navigating when you go off map.
Well said. Couldn't agree more.
This has been incredibly insightful. Thank you for taking us through that detailed exploration of planning and goal-oriented behavior. It really clarifies how AI moves from just processing data to actually acting purposefully.
My pleasure. It's a fascinating and absolutely critical area as these systems become more autonomous.
And for you, our listeners, the journey doesn't stop here. In our next deep dive, we're going to broaden the scope even further.
That's right. We'll be looking at multi-agent systems, MAS. What happens when you have multiple intelligent agents interacting in the same environment? How do they coordinate, compete, or collaborate? That's next time.
Sounds fascinating. Collaboration and conflict among AIs, so definitely stay tuned for that. Thank you once again for joining us on the deep dive.
Thanks for having me.
We invite you to subscribe to our channel, Tech AI and Beyond, to continue your journey into the fascinating world of artificial intelligence. We'll see you next time.